Graphs of functions. So we know that we have a function which is denoted by y equals f of x, right? The input is x, the output is f of x or y, right? So for each x, there's only one y corresponding to it. So we can form a pair of points. The input is, the first one is the x called x, and the second one is the output, right? You can use the input as the x coordinate, and the f of x or y values or f values as the output as the y coordinate. So that is represent a point in the plane. If we collect all the pairs, okay, let x run through all its domain, then we will form a curve. This curve is called the graph of a function f. Okay, so the graph of the function f is the collection of all ordered pairs x f of x, such that x is in the domain of f. So this is a typical graph, right? This is the graph for y equals f of x. So every point on any point on the graph, if this corresponds to x, then this point is x and f of x, right? Oh, x and y, but y is called f of x, so it's the same. They are the same thing. Okay, so this is called the graph. So we can, from the graph, we can identify or figure out the domain of the range, right? So you can see if the graph, this one, right? This is the graph, you can go up forever and go down forever. So this graph have the domain, which is from negative infinity or infinity. So that is all the x values, right? Because you can forever go down forever, right? So all the x value you can plug in. So this is all x values. What's the range? The range, let's look at the y values, right? The y-axis, the y values. So you can see all the y values corresponding to a point on the curve. So here is the range is also from negative infinity to infinity. This is all y values. Domain is all the x values. You can look at the x values. For arbitrary x value, you can the corresponding point on the curve. So x values can be plugged in, all x values can be plugged in. So the domain is also negative infinity to infinity. So now let's look at another example. If this is the graph, here is a circle, and this corresponds to one point, and here is 3. This point corresponds to y value is 3, and here is 1/2, and here is 4, right? Okay, so the domain is from the graph. The domain is the x values we can, because it starts from this point and ends this point. But here is a solid circle. That means this 1 must be included. and this is a hollowed circle. It means this 4 is not included. So the domain, all the x values you can plug in, which is from 1 to 4, but 4 is using the parentheses. The range, that means all the y values. So here the y value, the smallest y value is 1/2, and the largest y value is 3. So and these are the corresponding point to these two values. There are corresponding points to these two values. So these two values are included. So it's from -1/2 to 3. And the last time we have the vertical line test. We can use the vertical line to identify a curve is a function or not, right? Vertical line to identify. So this is just a quick review, and this is the vertical line, arbitrary vertical line. There is only one intersection point, right? And so this is the function. This is the function. But if you have this curve, this is not a function. The reason is, if you do a vertical line here, there are 3 intersection points. So it means one x value corresponds to 3 y values, right? So this is not a function. So now let's look at another definition, which is called the zeros of function. Function f. Okay. So we say, let's look at the formal definition. The zeros of a function f are the x values such that f of x equals 0. So in other words, the x-intercept, the y value equals 0, right? Or the x value such that the y equals 0. So that is actually the x-intercept, right? So for example, remark, if we have the x-intercept, x-intercept is at a and 0. Then x equals a is a 0 of a function f, right? Because it will make, when x equals a, y must be 0. So how to find it? You just set the function to be 0, then solve for x, right? So we need to find the zeros of g of x, which is 10 minus x squared. So here I use g. I know this here function usually to be f, but we know that f is the name of the function. We can use any other letters to replace it. So here I use g. Okay. Gx equals square root x 10 minus x squared. So we just set, to find 0, we just set g of x equals 0. So in other words, square root 10 minus x squared equals 0. So we square both sides, so you have this one equals 0. So x squared equals 10. X squared equals 10, so x equals plus or minus square root 10. So we have two zeros, right? One is positive square root 10, the other one is negative square root 10. But actually, if this is if you know the graph, or if you draw the graph using the graphing calculator, you will see this actually a half circle, right? Here is negative square root 2, and here is square root 2. So you have actually two intercepts, right? The x values for the two x intercepts are the zeros. And we also are interested in the increasing function, increasing, decreasing, or constant functions. We can identify these properties from the graph, okay? If, let's look at the definition. We say f is increasing if x minus x1 less than x2 implies f of x1 less than f of x2. If the input is smaller than the y values, the output would be smaller. This is the graph. x1 is here. This is x2. Right, here is y1. Here is y2. Right, y2 is f of x2. And y1 is f of x1. So from the graph, it's less than, right? So the smaller input will give you the smaller output. So this is called the increasing function. And we see a function is decreasing if x1 less than x2 implies f of x1 greater than f of x2. This is called the decreasing function. So this is the decreasing function. This is the x1, this is x2. And here's y1, here's y2. So you can see x1 is less than x2, but y1 is greater than y2. F is a constant function if for any two values x1 and x2, f of x1 is always f of x2. So the graph is just a horizontal line. For arbitrary x1 and arbitrary x2, no matter what the x1, x2 are, they have the same y value, which is a horizontal line. Let's look at this example. This is the graph. Negative 2, 2. This is 4. We stop here. And we stop here. Negative 4. Okay. So from negative 4 to negative 2, it's decreasing, right? So f is decreasing. When we talk about the increasing or decreasing, we're always using the open intervals. On the interval from negative 4 to negative 2, f is increasing. On the interval from 2 to 4, right? F is a constant. On the interval from negative 2 to 2. So what is the domain for this example? The domain is all the x values we can plug in. So it's actually from negative 4 to 4. Range from this graph is the corresponding y values. The smallest y value is, for example, if here is 2, and here is 6, right? And here is 4. So the range is 2 to 6, right? This is 2 to 6. There's no jump between it. Another property which is called the relative minimum and the relative maximum. Minimum and relative max or maximum. Sometimes some textbook call the local minimum and the local maximum. Okay, so now let's look at the relative maximum. What's the meaning for the relative maximum? If a function changes from increasing to decreasing at this point is C, f of C. If a function, I don't care about the other parts, I just say nearby this point, it will change from increasing to decreasing. So nearby, so that means it's a relative or local, right? Or local max. So this is the peak point, right? So we say that f attains its local or relative or local minimum or maximum. What is the maximum value? Which is maximum f of C at the point x equals C. Okay, so this is the relative maximum or local maximum or relative minimum or local minimum. So the graph at this point, it will change from the decreasing to increasing, which is the bottom point. Okay, the bottom point. So this is the C, f of C. And this is called the, then we say this function f attains its relative or local minimum, which is f of C at the point x equals C. So when we talk about minimum and maximum, we always means the f values, the function values, or the y values, right? This x equals C, it just gives you the position of this point. So here is one remark for the local or relative maximum and relative mean, or the local maximum and local minimum. The relative maximum or minimum is not necessary to be the maximum or minimum on the whole domain, entire domain. Okay? The relative means the local things nearby. We don't care about other things. Okay? For example, if you have this curve, this is the relative maximum. Relative, it will give you the relative max, and this is the relative minimum. But it's not the maximum because it's not the minimum because this point here is lower than this point, but this point is not the relative minimum because it can go down, right? It will not go up nearby. And here is the relative max. This relative maximum is not the maximum. However, this relative max is the maximum, right? Because it's the highest point for the whole domain. That is just the highest point nearby. So it's called relative. Then we look at another thing you want. It may be another thing you need for your future calculus class. So this is called the average rate of change. Okay, so if you have a curve which is from this point is x1 f of x1, so this curve is y equals f of x. Changes this to this point to that point, this is the x2 f of x2. So the average rate of change, average rate of change of the function f from x1 to x2 is actually the slope of the line through the point x1 and the f of x1 and x2 and f of x2. How to calculate slopes? That is these 2 points, so f values minus f values over x minus x values. But this is the, pay attention to the order of the index. And we denote it by MSEC. The slope of the secant line. This line is called the secant line. This is the slope of this line. Okay. So this is called the average rate of change. So one quick example. We want to find the average rates of change of the function f of x equals x cubed minus 3x from x1, which is equal to -2, to x2 is equal to -1. So the average rate of change is MSEC, which is equal to f of x2 minus f of x1 over x2 minus x1. So this is the f of -1 minus f of 2 over -1 minus, -2 minus -2. If you do your calculation, so when xf equals, so the denominator is what? Is 1. And f of -1, so it's the -1 plus 3. So this is 2 minus f of -2, so this is -8 plus -8, and -2. So this would be 4. Okay. So there's some applications for the average rate of change, which is if this x represented the time, so from time 1 to time 2, and f represented the position, okay, then f x2 minus f of x1, which is the distance change from time 2 to time 1 to time 2. And x2 minus x1 is actually what? Is the time used, okay, for this distance. So the distance divided the time, it will be the velocity. And that velocity is called the average velocity, right? Average velocity, this is the we have learned in the physics in high school. But then in the calculus you will learn from here, you can get some, if the velocity is different at a different position, then from this average rate of change, right, we can do something more fancy things to get, which is called the instantaneous rate of change. That is for the application of the velocity, which is called the instantaneous velocity. We have another property for the functions, which is called the odd and even functions. So the first thing is even function. We see f is even if you replace the input is negative x, then the output is the same as x. So in other words, if negative x, y, if x, y is on the graph, then negative x, y is also on the graph, right? The output negative x and y. So that is a symmetric about the y-axis. So the even function is always symmetric about y-axis. This is even, right? This is x. So here is x, f of x. And here is negative x. So this is the negative x, f of negative x, which is equal to negative x, f of x. Right? So they share the same y values, but x are the opposite direction. X are opposite. X values are opposite. So this is called even function. The even function is symmetric about the y-axis from the graph. And odd function, we say a function is odd if f of negative x would be equal to negative of f of x. So in other words, if x, y is on the graph, then if you replace x with negative x, then y must be negative y. The output must be a negative y. So that means and if x and y is on the graph, then negative x and negative y is also on the graph. That is symmetric with respect to the origin. So the odd function must be symmetric with respect to the origin, right? So this is x, f of x. So this point is fx and f of x. If you draw a line through the origin, and this must be negative x. So here is negative x, f of negative x. If f is odd function, so it must be negative f of x. Right. So it's symmetric about the origin. Okay. So now let's identify the function is odd or even. We must, if f of x equals 5 minus 3x, we must input the negative x. So the negative x is 5 minus 3 times negative x, which is 5 plus 3x. It has nothing to do with the original function, right? No relation between the original function. So this is the neither odd function nor odd even function. And if we have the h of x, which is 2x cubed plus 3x, so what is h of negative x? That is 2 times negative x cubed plus 3 times negative x. What's this? This is negative 2x cubed minus 3x. If you look at this one, this is if we put a negative in front, so it will becomes this one. What's this? This is the negative h of x, right? So this function is an odd function because h of negative x equals negative h of x. So how to identify even odd function? You just plug in the negative x to see what happens.